All right, today we're going to start thinking about Chapter 6. Remember that Chapter 7 is techniques of integration, how we can actually find antiderivatives, different methods that we would want to use to find integrals and antiderivatives. And Chapter 6, we're talking about applications of integration. So some things that you actually do, and many of them real-world situations that would require finding an antiderivative or finding an area under a curve or finding an integral. And so we're going to start with velocity, distance, and displacement right at the beginning of chapter 6, section 6.1. Okay, so before we get too far into that, let's just start with just a little thought experiment and turn it into a picture. So suppose that I'm a bug. Right? So I'm a bug, and this is the real line, and so this is 0. So this bug is walking around and it's stuck on this line. So it can go this way, it can go this way, it can do whatever it wants, but it's going to stay on this line. Right? Suppose that we're going to say that d at t is the displacement at time t. And displacement is different from distance in that it can be negative. Right? So what I mean is how far away from the origin I am at time t, but it could be positive or it could be negative. So in this case, this is the position on the number line at time t. So suppose that I had a graph that looked like this, time t, displacement at time t. If my graph looks like this, what does this actually mean as far as what my bug is doing? Right, so what this means is that the bug moved to the right for a little bit, and then it stopped, and it turned around, and its displacement started getting smaller. That is, its distance from the origin, its position at time t, started getting smaller, and at this point, it got back to the origin. Its displacement was 0, and now I have negative displacement, which means opposite direction. And so it moved into the negative x values, and then finally back to 0, and then moved a little bit forward. So for displacement, we may have negative values, and all that means is we're to the left of wherever we started. All right, so remember that velocity is not exactly the same as speed. But velocity is speed, but it might have a sign with it. So it could be positive or negative, just like displacement. Right? So velocity is the speed, but with a sign. Right? So velocity is the speed, but plus or minus depending on the direction of motion. So for the graph that we started with, something that looked like this. And if this was displacement, what would the corresponding speed graph look like, or velocity graph look like? Well, over here, it moved to the right, so which means that its velocity is positive. So my velocity is going to be positive. And what's happening with the velocity right here? Well, between time 0 and whatever time we have here, it moved, and it's actually moving much quicker than it is over here. And the reason that we can see that is because it got to the same distance. It got to the same distance away. If these are the same up and down as we are here, it took much shorter to get there than it did there. So it was moving more quickly over here than it was over here. Right? And so my speed would look something like this. And so I have a greater speed. Well, let's be a little bit careful. What's the speed right here when it turns around? Well, the speed is 0 when it turns around. So I have a speed that does something like this, where this point this point corresponds to that. So let's make that match a little bit better. Right, so this is a speed of 0, right here, speed of 0. And then at this point, it started moving left, so its speed goes negative. Its speed goes negative, 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 negative. Speed is moving left the whole time until we reach this point when it turns around again and starts moving right. In order to turn it around, it has to slow down and stop. And so its speed returns to 0 right here. So let's call this A, and this is A. And it returns to 0 right here at point B, and this is point B. But notice that it's up until here, it's been moving left because its displacement has been going down, and now it starts moving right again, so its velocity is positive. All right. Now, in terms of actual math, remember that the velocity is the rate of change of the displacement. So velocity is the derivative of displacement. And so we're going to say v at t, velocity at time t, is just d prime at t, the derivative of the displacement. Which means that I can say that a related equation, if I integrate both sides of this equation, I should get something that says this. The integral of the velocity is the integral of the derivative of the displacement, but the integral of a derivative is just the displacement itself. So this displacement at time t is the antiderivative of the velocity. So for example, if the velocity of my bug at time t is given by let's say t times t minus 1, which is t squared minus t. Let's find two things. The displacement at time t, b, the distance traveled. This is going to be different at time t. So this is my velocity, and okay, good. Keep in mind that for part A, it's displacement at time 0. Let's also say that we're given that the displacement at time 0 is 0. So it starts at the origin. Its velocity at time t is t squared minus t. So its displacement at time t is the antiderivative of the velocity, which is the antiderivative of t squared minus t, which is t cubed over 3 minus t squared over 2 plus c. Now, so we get this plus c at the end. How are we going to figure out what this constant is at the end? Well, we're given that the displacement at time 0 is 0. So displacement at time 0, according to this, is just 0 minus 0 plus c, which is c. But we're told that that's got to equal 0, so c is 0. And I can say that the displacement at time t is just t cubed over 3 minus t squared over 2. Okay, now let's be careful, right? Because let's graph this displacement. So I'm not going to put this on the screen, but if I were just to graph this function, t cubed over 3 minus t squared over 2, this is what it looks like. Right, so I just graphed it with a standard zoom and then zoomed in just one time because to notice that in fact it does go below the x-axis. So what does this actually mean? This means that my bug moved left to begin. This is my displacement at time t. So it moved, and since it's below the x-axis, it moved left to start. And then at this time, whatever that is, we can figure that out in a second. It actually, its displacement got back to 0, and so then it started moving right. So when displacement is above the x-axis, it's moving right. Positive displacement means that it's on the right of where it started. Negative displacement means that it's on the left of where it started. Okay, so we can actually figure out what that is, right? Because if I set this equal to 0, I can factor out a t squared, and I get t over 3 minus 1/2. And so this is equal to 0 when t is equal to 0. And it's also equal to 0 when I get 1/2 times 3, which is 3/2. So this is at 1.5. So at 1.5, at time 1.5, it got back to the origin, and then it was on the right afterwards. Okay, now the next part B, find the distance traveled. Well, that's different. All right, so the distance traveled is different, and let's think about why. Well, so velocity, remember, was t squared minus t. T squared minus t. What's that velocity look like? If I were to graph that velocity, that's t times t minus 1. So it goes through the origin at time 0. It goes through the origin at time 1. It's a parabola that opens up. So this is what the velocity looks like. So this is saying velocity 0 at time 0, velocity 0 at time 1, negative velocity in between, which means that it's moving left. If I have a negative velocity, it's moving left. At time 1, it stops and turns around and moves right. Right? So if I ask for the distance traveled, well, the problem is, so here is our velocity. We also had our displacement that we looked at, displacement at time t. Notice that, remember that looks something like this. At 1.5 now, not at 1, it went back through the x-axis. This time 1, 0 velocity corresponds to this point where it turned around. Its velocity, its displacement stopped getting more and more negative and started going back towards 0. Right, so this corresponds to that time right there. But this is not the distance traveled. If I want to know the distance traveled, at this time right here, time 1.5, displacement is 0, but I haven't moved 0 units. I've moved all of this time. I just moved left and then got back to where I started. So if I'm asking about the distance traveled, that's a different question. If I want to know the distance traveled, what I actually need to know is I don't care about the pluses or minuses. Right? So negative velocity just means I'm moving left. But if I don't care about that, and I just want to know how far I've gone, let's notice that distance is, instead of the integral of the velocity, it's going to be the integral of the absolute value. I don't care about whether it's plus or minus, and this I'm going to call the speed. And the speed is how fast it's moving. If I integrate the speed, then I'm going to get distance. Integrate velocity, I get displacement. But again, here's V. Here's V at time 1. What does this mean? Integrating the absolute value, getting rid of the negatives. In terms of practical use, what that means is this is where the velocity is negative between 0 and 1. So what I really want, so the distance traveled, distance at time t, between 0 and 1, right? So so this should be absolute value of t squared minus t dt. That's fine, but integrating an absolute value is very tricky. So let's see how we're going to work this. Let's ask a more specific question first, and then we'll come back and answer the general one. What is that? How far has the bug moved at the following times? Let's say t equal 1/2, t equal 1, t equal 1.5. Here's our velocity equation, or here's our velocity there's our velocity function, v of t. So at time, this is at time 1. So at time 1/2, how far have we moved? Well, I want to integrate, right? But I want to, so I'm going to integrate so that at t equal 1/2, I will integrate from time 0 to time 1/2. This is our function, t squared minus t, but since it's below the x-axis, I actually need to make it a positive number. Right, so this is going to be a negative value because it's below the x-axis. So I actually need to make it negative. That's what absolute value actually does, right? If it's negative, if this is going to be negative, if I want absolute value, then I just need to change that from being negative to positive. So this is going to be our answer for the distance traveled at time 1/2. At time 1, it's exactly the same because it's below the x-axis the entire time. At t equal 1, we'll integrate from 0 to 1 of our velocity. But since that's below the x-axis the entire time, that's going to be a negative integral, and we need to make it positive to talk about distance. At t equal 1.5, well, now we have a little bit more of a problem, right? Because between time 0 and 1, it's below the x-axis, so I can integrate from 0 to 1 of t squared minus t dt. That's going to be a negative number. If I want distance traveled, I need to make it positive by making this, by taking the negative of the entire piece. And then I need to talk about what happens from 1 to 1.5. So then I need to add 1 to 1.5 of t squared minus t. This is already positive because the velocity is positive across that region. So when we talk about distance, sometimes we need to break it up into different pieces. The pieces on which the velocity is negative, and the pieces on which the velocity is positive. Okay. So that's all we need to say about 6.1. I'll see you next time for 6.2.